So our project is MultiAudio, a multi-threaded audio processor through which we enhance microphone input through digital signal processing. Problem statement. Raw microphone input is often noisy, meaning it can have distracting background sounds, imbalanced, as in the input frequencies could be harsh or undetectable, inconsistent, the volume can alternate between being too low or too high, and sibilant, full of grating S sounds when you say words with S in it. So real-time audio processing demands low latency to prevent audio artifacts like crackling, buzzing, or delay. It also demands high-quality transformation without distortion and parallel computing to prevent system overload. The problem with traditional software is that it's often bulky, resource-intensive, or hard to use for beginners. So our solution is to build a real-time multi-threaded audio processor that enhances the microphone input through 4 key effects, being noise reduction, frequency balancing through an EQ, dynamic range control, and sibilance reduction. And we seek to emphasize performance via low latency and high quality, user accessibility through an intuitive GUI, modularity, having the modules process independently from each other, and we'll use C++ threading and modern digital signal processing techniques for all of these.
So why it matters is because it shows how audio effects like de-essers, equalizers, noise gates, and limiters can be implemented and analyzed at low level using C++. By measuring and visualizing how each processor changes the audio signal over time, we can better understand their impact on clarity, balance, and loudness. It's a hands-on way to bridge digital signal processing theory with practical real-time audio applications, something that's essential in live streaming, virtual meetings like Zoom, MS Teams, Discord, podcasting and voiceovers, gaming voice chat, and voice assistants.
So for our target audience for this project, we include content creators, streamers, podcasters, gamers, and developers who want to improve voice quality without relying on bulky or expensive third-party software. Students or professionals interested in audio processing, real-time systems, and multi-threaded application design may also benefit from our project. For our system architecture, we had a 2-thread architecture. We had audio input-output thread, a high-priority thread, which manages hardware buffers and strict timing. And additionally, we had a processing thread which applies effects chain sequentially. Thread communication was utilized via buffer queue with condition variables. Benefits of this system architecture include separation of time-critical input-output from CPU-intensive processing, reduced risk of audio dropouts while maintaining quality, and we also had an optimal use of multi-core processors.
Yeah, for our processing pipeline that we're using, it all starts in our main thread where we're launching the UI and taking in user input to update the effects. Then we're using a audio input-output thread, which has an RT audio callback function, which gets the raw mic input and then writes it into the input buffer. From there, our effects processing thread is constantly popping from that input buffer and applying our effects sequentially. So that goes for noise gate, EQ, de-esser, and into the limiter. That order is intentional because we want to make sure that the noise gate cuts out frequencies before we start changing and affecting the gain on those. From there, we after the limiter is complete, we write the output audio to the output buffer, in which the audio input-output thread pops from the output buffer and writes the audio data through the speakers.
Technology used. So the programming language we used was C++ for performance and multi-threading. We also use RT Audio library for real-time audio input-output, FFTW for frequency analysis and fast Fourier transform, and thread safe queues for thread communication.
So here's our total DSP audio processor effect suite, as we've teased before. So the noise gate is the first effect, and the noise gate mutes low amplitude signals, background noise, like a gate opening up and closing whenever the noise is loud enough to allow it through. Next, we have a 3-band EQ that allows users to boost low, mid, and high frequencies from the microphone input, which can create anything from a podcast sort of effect to an old-school radio. Similarly, we have a de-esser, which reduces high-frequency sibilance, which occurs from 4 to 10 kilohertz. And lastly, a limiter, which prevents clipping by capping the peak amplitude that the input can occur at. All effects are implemented using the fast Fourier transform-based spectral processing, which is pivotal throughout DSP, and we have a user-adjustable GUI using various parameters.
So in order to access this shared memory between multiple threads, we're using a custom audio buffer class. So this class acts as the communication channel between our real-time audio input-output thread and the effects processing thread. So it's important to set this up as a thread-safe queue, so we can add mutexes and atomics to ensure that there's not going to be any race conditions with our threads accessing shared memory. This helps isolate the critical input-output pipeline from the more computationally intensive effects thread. So this prevents any latency in our application. We have 2 global buffers, one for input and one for output. These are used by multiple threads to ensure a seamless audio pipeline.
So the noise gate, what and why? As said previously, the noise gate works by attenuating signals below threshold to remove room noise. So in plain English, that means we might have cleaner audio signals for later processing that will eliminate fan noise, keyboard clicks, and other room resonance that we don't want picked up. While it does that, it preserves voice frequencies and cuts the noise, so we get only the desired output. So how does it work? The noise gate works by first converting the input audio signal from the time domain to the frequency domain using the famous fast Fourier transform formula. More specifically, it splits the frequency spectrum into 4 separate bands and calculates their energy, which could be thought of as a perceived volume. If the energy doesn't meet the specified threshold, the gate closes and the audio is silenced for that band, as in it's not let through the gate. Vice versa also applies to where if it does meet the specified threshold, the gate opens and the audio is let through and you can hear it in the output. And so this is all smoothly adjusted using gain over time and release, attack and release values that can be adjusted for your own microphone and room environment.
Yeah, so the next effect that we add in the chain is a 3-band EQ. So this, kind of similar to the noise gate, splits our audio into a low, middle, and high frequency band. This allows independent gain control for each band, which modifies the output volume for different frequencies. So you can either lower or increase the volume for different frequency bands. There's a customizable gain levels through the graphical user interface, so you can customize those to your liking or enable or disable the effect. So this works pretty similarly to the noise gate, actually. So we're splitting up the audio spectrum into separate regions. This time we're using 3 separate regions instead of 4. We use a window function to help reduce artifacts between bands due to some sharp cutoffs between the frequency ranges. We convert the audio from time to frequency domain with a fast Fourier transform, in which we loop through each frequency component and apply the respective gain level for whichever band that belongs to. Then we convert the signal back to the time domain with a reverse Fourier transform and blend the result with the raw input to help avoid sudden jumps in audio volume.
So a de-esser, what and why? A de-esser works by detecting and reducing the level of specific high-frequency sounds associated with sibilance, usually in the 4 kHz and 10 kHz range, or 4 to 10 kHz range. It enhances clarity and reduces listener fatigue and improves overall vocal quality. The use cases for this can be in podcasts, live commentary, interview, and virtual meetings. When those frequencies exceed a set threshold, the de-esser automatically lowers their volume by applying gain reduction and essentially ducking them in real time. So more onto how it works, it uses FFT to convert audio into frequency domain. It then identifies and reduces amplitude in the 4 to 10 kHz band. It inverses FFT reconstructs the inverse FFT reconstructs time domain audio. We implemented this using C++, as said many times before. And the key parameters for this is that the frame size is 2048 and there is a 6 dB reduction.
Limiter, what and why? Limiter is a type of dynamic range processor that prevents audio signals from exceeding a set amplitude threshold, which protects against clipping and distortion. Its purpose is to ensure audio remains within a defined loudness range, which is crucial for maintaining clarity and preventing speaker damage. Why it matters? It keeps peaks in check without destroying dynamics. It's vital for live audio streams where unexpected loud sounds can degrade quality, and it acts as a safety net for the other effects as it comes last in the pipeline. So, how it works. We have threshold control, which samples above a certain amplitude are automatically reduced. It uses look-ahead processing, which allows the system to gently respond to sudden peaks. That works by using an attack and release time to determine how quickly it responds to loud sounds and how quickly it stops limiting once the sound is back to normal range. It also has dynamic gain adjustment, so if a sample is below the threshold, it passes unchanged through the limiter. If it's above the threshold, it's multiplied by a calculated gain to reduce it. It also utilizes smooth gain transitions, which uses exponential moving averages to interpolate the gain changes. As said many times before, it uses efficient C++ implementations, which are multi-thread safe and optimized for real-time performance, and it operates within a dedicated processing thread to minimize latency.
So here's our GUI demo for MultiAudio. And so as our effects are applied in a sequence, one way a sequence can be thought of as a stack where effects are applied one at a time. So the most intuitive way we thought to approach this was having an effect stack menu on the left, where you can click through each of the effects, and on the right you have a window with effect-specific controls, such as a checkbox to enable, and the parameters for the function you're currently adjusting. So for instance, in this noise gate screenshot, that would be threshold, an attack meter, and a release meter.
So to begin by talking about the noise gate results in testing, the purpose of our test was to evaluate how well it suppresses low-level background noise. We did this by comparing RMS values of the raw and processed signals. In the initial and final frames, we saw that the processed signals starts later and ends more abruptly. This shows that input below the threshold, like anything under about 0.02, is either muted or heavily attenuated. This confirms the gate is activating as expected based on the signal level. In the middle of the signal, the processed RMS remains consistently lower than the raw signal, meaning weaker frames are being gated out while stronger ones pass through. Then in the decay phase, we notice the processed signal drops off very sharply as RMS declines, which points to aggressive gating behavior as soon as the signal drops below the threshold. Overall, the noise gate is successfully reducing background hiss and noise in quiet parts of the audio while preserving the dominant, more prominent content. So if you can play. For the limiter testing, the goal was to assess how it affects dynamic range and peak amplitude. In the early frames, the raw signal shows large fluctuations between 0.4 and 0.5 RMS, which indicates loud transients. The processed signal, however, is capped closer to 0.35 to 0.4 RMS. This confirms the limiter is effectively taming peaks without impacting the rest of the waveform. The RMS envelope also flattens, which further suggests controlled peak suppression. In the later frames, the RMS values of the raw and processed signals converge. This shows that the limiter leaves quieter sections untouched, which is ideal. Overall, the limiter performs as expected. It reduces peak levels to prevent distortion, but it still keeps the natural shape and timing of the original signal. So for the 3-band EQ, we did just use one sample and doubled the bass and then the middle and then the treble for that same sample. So the purpose of this was to assess tonal adjustments by applying 2 times the gain to each of those sections individually. And we used an instrumental track to clearly isolate frequency band effects. So for the bass boost results, we noticed that the RMS significantly increased in low frequency sections, such as the kick drums, bass lines, etc. It enhanced rhythmic depth and warmth, and it also produced a fuller, more grounded audio profile. So then for our mid-range boost results, we noticed that the RMS rose consistently across most frames, boosted melodic elements like guitar, piano, and harmonic content. It resulted in a stronger, richer tonal body throughout the track. Then moving on to our treble boost results, it was more modest but focused RMS increases, especially in high frequency regions like any harmonics. It improved brightness, clarity, and articulation. Subtle enhancement without overpowering the mix, basically. Overall, the RMS shape and temporal dynamics were preserved in all cases. There was no distortion or artifacts that were introduced, and it all demonstrates precise and transparent gain control per band. So this is our de-esser test results. These are a little bit more difficult to notice the changes than the other effects, mainly because it's only looking for a very specific S and SH sound. And those differences can be seen by the green circles that you can see over there. We basically focused on reducing sibilance and evaluated performance by comparing the RMS values. In the early frames, we can see a clear drop in RMS, which indicates effective suppression of harsh S and SH sounds. In the mid frames, peaks in the raw signal, especially in the 4 to 10 kHz sibilant range, are noticeably attenuated in the processed version. This confirms the de-esser is accurately targeting the frequencies we want to reduce. By the late frames, the RMS reduction continues, which shows that the de-esser is consistently working throughout the entire clip. Overall, as before, the general shape of the RMS curve stays the same. That tells us that audio's natural dynamics weren't distorted, just the unwanted sibilance was reduced.
Spotting subjectively tempting suspicion of Turkish sugar trimming sustains substantial turbulence of flatlined filth. Spotting subjectively tempting suspicion of Turkish sugar trimming sustains substantial turbulence of flatlined filth.
Challenges. So there were some challenges when trying to synchronize real-life threads with minimal latency. There were also issues when avoiding or removing artifacts, which are like audio anomalies, while applying fast Fourier transform, like crackling, clipping, and other volume issues. We also had problems with stereo handling without phase mismatch and balancing CPU usage versus audio responsiveness. Conclusion. So we found that sequential chain of effects like noise gate, equalizer, de-esser, limiter enhances audio quality. And that single-threaded effects processing reduces complexity and latency. Also, with an intuitive interface for real-time control and adaptability, This creates a user-friendly design. It's also suitable for broadcasting and streaming and recording, anything that has to do with audio processing. And this helps support future enhancements like adaptive thresholding and multi-band processing.
Hello again. Now I'll be demonstrating how to run and compile our multi-threaded audio processor MultiAudio from source on Windows. So once we've opened a terminal and navigated to the directory where we want to install the project, we can go ahead and run a recursive clone on the repo. And that might take a second because we have to also clone submodules for the GUI libraries. Once that's done, we can change directory to the project's directory. And now, before we proceed and build the project ourselves, we want to make sure that all of our dependencies are installed. Now, this will differ per operating system, but on Windows, I prefer to use MSys2 MinGW64. And once we open this terminal, I will run the command pacman-syu to update our packages. And because mine are up to date, there's nothing to do. Next, we can take this command from the repo instructions and download all the required packages for running the project. And I already have them installed, or these packages don't matter for building it right now. So we'll go ahead and close that. Now we'll see which files are available in the project directory, and we have this build.bat script. So we'll run that to build the project. And all of these error messages are just for debug purposes. They're absolutely normal and not fatal. And now we've reached the successful build. So let's go ahead and run it by opening the multiaudio.exe program. And so now you'll be able to hear yourself through the multi-audio processor. So currently we have the effects stack that we described in the PowerPoint, which is the noise gate, the de-esser, the limiter, and the 3-band EQ. So I'll go ahead and demonstrate these one by one by adjusting the parameters. Now you might have noticed that in my microphone you can hear my computer fan. That's actually intentional so I can demonstrate the noise gate. So now that if I hit enable and I increase the threshold, you'll slowly hear it fade out. However, if I speak into the microphone, only my voice activates the noise gate. And now my computer fan won't constantly be transmitting the low frequency hum. And of course you can adjust these attack and release parameters according to your environment and your microphone. But of course that might mess with our audio, so I'll turn it off. Next is the de-esser, which is intended to reduce sibilant S sounds, which can often be pretty jarring. So once you get these parameters for the start and end frequency right, you can hear a pretty substantial reduction in S sounds. So let's go ahead and try it. So now if I say a lot of S sounds, and I increase the reduction just to the right point where there aren't any artifacts, there's a big difference between this S and this S. And of course, these effects can be stacked in tandem. So if I enable my noise gate and my de-esser, you can use both, of course adjusting to remove artifacts as necessary. Next we'll move on to the limiter. And the limiter is enabled or intended to prevent audio peaks from exceeding a certain threshold. So for instance, if I'm pressing my keyboard and that's very loud and audible, I can enable the limiter and drag the threshold so that audio is cut out. And of course, we can adjust the attack and release parameters just like we did in the noise gate. Lastly, let's go over the 3-band EQ. The 3-band EQ allows you to control the gain of the low, mid, and high frequency ranges of your microphone input. So we'll go ahead and enable this, and if I want to make the lows more dramatic, I can simply boost that, and my voice will suddenly sound much more boomy. Or I could remove the low ends entirely, which creates some kind of radio effect. Likewise, I can boost or lower the mids to EQ accordingly, and do the same thing with the highs. So you can get some pretty interesting results there. And let's go ahead and just apply all of the effects just to get the most dramatic changes. And as you can see, we have my voice coming in and out because of the limiter enabled, and we can turn the de-esser on, adjusting to remove artifacts as necessary based on the start and end frequencies of the sibilants. And yeah, that just shows all of the effects working sequentially on their own thread, where the input effects and output threads are working in parallel.